So now we're going to start looking at two-dimensional motion, but not objects that are projectiles, things that are shot or thrown through the air. Let me give you an example of what I mean. Consider a rocket ship taking off, and it has an engine to it. And the engine is providing a constant constant velocity. It is going that direction, and we'll say 500 meters per second. Well, is that a velocity in the x or the y, or both? The answer is both. It is going forward and up at the same time. So this is motion in two dimensions. It's moving in x and y at the same time. This is a little different because gravity is not what is causing the motion to change in the y dimension. It's the engine of the rocket. So let's look at some examples and how we solve these problems. What I need you to do is fill this out step by step as I do it, and this is going to work as a guide for you to help you solve through these problems on your own. So let's take this first example, plane taking off with a constant velocity. So it's not accelerating, it's not speeding up or slowing down. It's a constant velocity of 100 meters per second. But it's at an angle of 25 degrees up from horizontal. So it's going from horizontal, it is rising up at an angle of 25 degrees from the ground. I've drawn the diagram for you. You are going to, at some point, have to draw these little diagrams for yourself to be able to visualize what's going on in these situations. For now, you've got it here. So the question to ask, if the plane's velocity is 100 meters per second, is it in the x direction, forward, or is it in the y direction, upward, or both? The answer is both. It is going forward and up at the same time, but the plane's velocity is 100 meters per second, and we're going to use some SOHCAHTOA trigonometry to determine the velocity of the plane in the forward direction. This makes a right triangle. And I know the hypotenuse is 100 meters per second. That's where the plane is actually traveling. That is its actual total or resultant velocity. Well, some of that velocity is going forward. That is the x. Some of it is going up in the y. We can use some basic trig here to find out how much of this velocity is the going forward and how much of it is the going up part. I've got this angle. I've got the hypotenuse. I've got the adjacent side is represented by x. So the adjacent side deals with the cosine part of this. So the cosine of 25 is the adjacent x over the hypotenuse 100. So the x velocity here is 100 times the cosine of 25. So I put that in my calculator and I get an answer of 90.63. So the forward velocity is about, we'll call it 91 meters per second. Now we can do the same thing in the y direction. That is the opposite side compared to the hypotenuse. So I'm going to use the sine of 25 is the opposite over the hypotenuse. So my upward velocity is going to be 100 times the sine of 25 degrees. And that value comes out to be 42.2. So we'll call it a nice even 42 meters per second. Now this kind of makes sense. 25 degrees is a lot more going in x than it is in y. So we would expect the y velocity to be a lot smaller than the x. Now, how far forward has the plane traveled in 72 seconds? We're looking for forward. Now we can use this formula here because this is a constant velocity. There is no acceleration in either the x or the y because it is a constant velocity problem. Well, now I know the velocity going forward is 91. I now know the time is 72 seconds. Multiply 91 times 72 and you get 65.52 meters it has gone forward. Now, how high is the distance in the y direction? as opposed to our projectile problems, we can use this formula here for the y dimension as well as the x, because once again it is a constant velocity. It is going the same speed the whole time. And that velocity is 42 meters per second going up. And now it is, after 43 seconds, do 42 times 43. And you get an answer of 1806. That is how high the plane is up. Let's take a look at a different example. I've got a soccer player running from one corner of the field to the other corner. We have the dimensions of this particular soccer field. It takes the player 15 seconds to go from here to here. Now, was he moving in one dimension or two? The answer is he's moving in two, because he's going forward and across the field at the same time. That's motion in two dimensions at once. And it takes him 15 seconds to cover this distance. What is the player's velocity down the field? We'll call this the x direction. We want to know the velocity in the x direction. Well, that is the distance in the x direction with the time. Well, the distance that we moved in the x was 105 meters, and it took him 15 seconds to do so. So we take 105 divided by 15, and we get a velocity of 7 meters per second going this way. Now, going across, let's think about this for a second. In those same 15 seconds, the player doesn't go nearly as far in the y as he did in the x. So I'm going to expect that my velocity going across the field has got to be less, because I'm covering less distance in the same amount of time. But let's see, velocity in the y is a distance in the y divided by the time. Once again, we can use this because there is no acceleration. The player is going at a constant velocity. This is not a gravity where the y dimension is changing because of the acceleration due to gravity. My distance in the y was 68 meters. The time, well, it's still 15 seconds. So now we have 68 divided by 15. And that gives me a velocity of 4.5 meters per second, which once again kind of tracks with what I said to begin with. My y velocity is probably going to be less than my x, because in the same amount of time, I cover less distance this way than I do this way. Now this question, how fast was the player running? Remember, the player wasn't running 7 meters per second. He was running that fast forward and this fast across. Well, what we're looking for here is the resultant velocity. Remember, the resultant is kind of the combination of the two aspects, or the two dimensions of motion. So how do I get this? Well, I've got a right triangle. I want to know the resultant. I know that this side, my velocity was 7. This side was 4.5. How do I find the resultant? Well, that's Pythagorean theorem problem. My resultant velocity is the square root of 4.5 squared plus 7 squared. There you can see my math. I get a resultant velocity of 8.3 meters per second. Once again, my resultant velocity should be the biggest number because it is the hypotenuse, and it is bigger than that, and it is bigger than that. Now, what is the player's direction of motion? Well, here's where this gets a little tricky. We know he's going across the field, but we want to get specific. Let's talk about this angle here. What angle is that? Well, we can do some trigonometry and we can figure out what that angle is even with the distances. This is the adjacent side and this is the opposite side. With the opposite, the adjacent, I can use the tangent function. The tangent of that angle is the opposite, 68 divided by 105. That 68 divided by 105 is 0.647. Well, that's what the tangent of the angle is. So I have to take the inverse tangent, 0.647, to figure out what that actual angle is. And I get an angle of of about 33 degrees. Now, how do we describe that angle? That angle there is not north, south, east, and west. I don't know which way this field is pointed. So how am I going to describe that? That angle is 33 degrees measured away from where? We can't say horizontal because the surface is flat. I would describe this as 33 degrees away from the sideline because that's how that angle is described. Here's the sideline, and he went at a direction that is 33 degrees away from the sideline. Now let's take a look at this boat going across a river. The boat's engines provide a velocity of, or give the boat a velocity of 10 meters per second, and of course the engines propel the boat forward. But the water in the river is also pushing the boat this way. So the boat has a velocity forward by its engine, but has a velocity this way because it's being carried by the water, and that water has a velocity of 4 meters per second. And we know the river is 125 meters across because it's given to us. How long does it take the boat to cross the river? Well, that's the 125 meters wide. Well, there it has a velocity going that direction of 10. Let's go ahead and call that the x direction. We'll call this the y direction. I can use this formula here because there is no acceleration. The boat has a constant velocity. My velocity provided by the engines is 10 meters per second. The distance across the river is 125 meters. So the time ends up being 12.5 seconds. That's how long it's going to take the boat to go this distance because its engines are providing it a velocity of 10 meters per second going this way. It doesn't matter how fast the water is moving. The engines push the boat from one side to the other. Now, does the boat wind up straight across the river? No, because as the boat is moving this way, the water is going to push it this direction. But its time to cross the river is dependent on the boat's engines. It has nothing to do with the water. Now, how far does the boat move this way down the river? We can see that it's going to get pushed down here because it has a velocity that direction. Well, we'll call that the y. We want to know the how far part. Well, we know the velocity in the y is 4 meters per second. We now know it takes 12.5 seconds for the boat to be in motion, and it's going to stop when it gets to the other side of the river. So it's going to stop over here somewhere. And that's the same time in x and in y. Well, what's the y distance? We take 4 times 12.5. That equals 50 meters. So the boat winds up 50 meters this way down the river. And if I wanted to actually draw this, I would probably draw it right about there. Because if the river is 125 meters across, I'd want to draw a smaller distance in the y. So the boat does something like that. That's how the boat moves. We want to know what is the boat's resultant velocity, both magnitude and direction. So the boat is doing something like that. We know its velocity this way was 10. We know its velocity this way was 4. What is the resultant? That's Pythagorean theorem problem. My resultant velocity is the square root of 10 squared plus 4 squared, which is the square root of 116. Take 116. All right, sorry. Square root of 116. Sorry. So we'll call that a nice even 11 meters per second. Now that's the magnitude. That's how fast it was going. But which direction was it moving? And we want to be exact. We want to talk about this angle here. Well, how do we get that angle? Well, this is going back to Sokotoa. We know the opposite and we know the adjacent. That's my tangent function again. My tangent of that angle is the opposite for over adjacent. So the tangent, we can go ahead and do this all in the calculator. We can do 4 divided by 10. That's 0.4. But that's the tangent of the angle. The angle is the inverse tangent of 0.4. So I'm going to say the inverse tangent of 0.4, and that is, we'll call that nice 22 degrees. Once again, how do I describe that angle? It's 22 degrees downriver. Because think, I should normally go straight across, but I don't wind up straight across. I wind up at an angle of 22 degrees down from straight across the river. And then we would say that as being downriver. So for our final example here, we've got a car going up a hill, and we know the car is traveling 10 meters per second, and it's on a hill that has an angle of 20 degrees up from horizontal. We want to know how long does it take the car to reach the top of the hill if the hill is 60 meters tall. Well, we know how fast it's moving, but we don't know its distance. If we talk about this velocity here, this is how fast the car is moving from here to here. That's in this dimension of motion, the hypotenuse. But we want to know how long does it take for it to get to here. That's 60 meters up. Well, that's an up distance. That doesn't correspond to our velocity on the hill. So I need to know an up velocity because I want to know how long does it take me to get to that point high. Well, if I know that this velocity is 10, can I figure out the y velocity? Go back to my Sokotoa. I know my hypotenuse is 10. This is the opposite side from the angle. So I'm going to look at my sine function. The sine of 20 is the opposite over the hypotenuse. So my opposite, my up velocity, my Vy, maybe I should put that as Vy, is 10 times the sine of 20 is Vy. So 10 times sine of 20. So my Vy is 3.4 meters per second. So we're going up at 3.4 meters per second. But how high up do we go? We go up to 60. Well, how long does it take me to go up that high? I'm going up at a rate of 3.4 meters per second. I'm going up to 60 meters. How long does that take me? 60 divided by 3.4 takes me about 17.6 seconds to go up that high. How could I get up there quicker? Well, if I increased this, I would make it to the top faster. If I wasn't going as high up, if the hill wasn't as higher, the time would be lower. So these are all examples of motion in 2 dimensions where it's not gravity that is determining the velocity or the motion in one of those dimensions.